Okay. So, if you recall, in the last chapter, okay, we discussed the issues which were really cannot be explained using classical mechanics. When we say classical, it means classical Newtonian mechanics, okay, and ideas which are non-intuitive ideas, such as, for example, the discreteness of energy, had to be used, okay, in order to explain at least three results, three experiments, okay, and they were actually quite successful in doing so, okay, namely the quantum scattering, the photoelectric effect, and the last one is the quantization of energy in order to explain the black body radiation. Okay, so Max Planck, Albert Einstein, and Compton, and we discussed also about Heisenberg, his famous equation, which I repeat, you don't need to remember it. Just take a look at it and try to see what it does. You have the time derivatives. You have psi, which is very important, which is called the wave function. The psi square is a probability. So we discussed this transition from a deterministic approach to a wave approach coupled to a probabilistic approach, okay, which is quantum mechanics. Now we're going to go into the more of the atomic physics, and the idea is we're going to start with a very simple treatment, okay, and we're going to complicate it a little bit more. But even with this simplification, you will see that we will be able to explain the whole Mendeleev table of material which exists on Earth and of course in the universe. Okay, so that's the idea. Is really the idea to go towards the explain why, for example, why copper is a very good conductor and why germanium is a semiconductor, and all these properties which come from their atomic properties. So this chapter is basically about atomic physics, and we're gonna deal with this. What we're gonna deal with that. So atomic physics is basically, so it deals with the physics of the atom. Okay, it deals with the physics of the atom and the arrangements of the electrons around the protons. Okay, and hereafter we consider them as isolated atoms. So basically, we do not consider atom interacting with each other. Okay, so we're not, and consequently, neither we're going to be concerned with molecules, or basically more than one atom acting. Okay, the hydrogen atom, we're going to take it as the simplest case because it has one proton, one electron, which is going around. Okay, and with this just one atom, if the idea is that if we are able to develop the right theory, then we will explain all the atoms. And this is why quantum mechanics is so strong and is so powerful in explaining atomic scale processes and shed a different light on the universe around us, especially on these time scales. So the hydrogen atom is an ideal system because it's very simple. The same theory can be applied for helium 1+ or lithium 2+. Basically, you have a proton and just one electron. That's the idea, is just to have one electron around the nucleus. Right? For helium, you have 2 protons, 2 neutrons. For lithium, you have 3 protons, 3 neutrons. But if you ionize, if you remove 2 electrons, you have 3 protons, but 1 electron, which is going around the nucleus. Okay, so where do we start? All right, so we're talking about the atom, right? So let's a little bit do some historical facts and then to see where we are now, our understanding now, and of course the jump into explaining from the hydrogen atom into the whole Mendeleev table. So the first idea of the matter in general, if you look at a solid, okay, look at this pen, and then you imagine that this pen is formed of small spheres is done by our friend Mr. Newton. Again, sorry about that, but definitely he's a genius. His idea is that the atom is a sphere. So basically, if you put these spheres close together, then you have a metal. If these spheres, they are able to maintain their link together, but they can move, that's the liquid. And if these spheres, they are each one going in different direction, that's the gas. So the sphere idea was actually quite successful until until we discovered electricity. So, okay, now I have these atoms. I have copper, if you remember our friend Mr. Copper. So the copper metal, and there are electrons. Okay, so where do the electrons come from? All right. The idea by J.J. Thomson, as shown here, is that these electrons, they come from the atom. So yes, I have a sphere. So we remain in the Newtonian model for a sphere. But now this sphere, inside it, there are these blue dots, which are the electrons. And these electrons, they are able to travel inside the solid, okay, moving from one side to the other. And this could explain one, the remainder, you have the atomic picture by Newton. Of course, he did not see an atom. Okay, it was only by his imagination. And then the idea by J.J. Thomson, which now add, how can I, with this idea, how can I explain electricity? Okay, and the fact that we have these charging, etc., etc. So that's what Thomson contribution is. Next step, we come, so basically Newton, Thomson, and now we're gonna go with Rutherford, Geiger, and Marsden. Okay, so what did these guys do? So they wanted to understand this atomic scale. And in order to understand this atom, what they did is a very simple experiment. So they had this source of alpha particles. Alpha particles, these are helium-2+, yani 2 protons, 2 neutrons, and no electrons around it. Okay, just the protons. And so they bombarded a target through a LED screen. LED screens, what it does, it only allow the helium-2+ or the alpha particles which are going in one given direction. So only these going in one direction, they are allowed to hit the the gold foil. It was used. The gold foil was used. Okay, and so they interact with it. And so the idea is that, okay, I have this atom. They come. I have these alpha particles. They will come, and by interaction with the atoms, they will scatter. In order for me to understand how they scatter, I'm gonna put a viewing screen on the back to see how they scatter. Okay. And so what they found is that, well, indeed, the idea is that these alpha particles, they interact with these atoms and they are deviated. Okay, so they come in, they interact with the atom, and they deviate. Okay, and so they have this deviation, which is okay. Everybody is happy so far, until and probably by chance they put this viewing screen not at the back of the target, but also on the front. Okay, wow. So if you have particles on the front, which are, if you have alpha particles on the front, these are like reflected particles. Okay, reflected particles. This means that this particle here came. This is my atom. Okay, it stopped and then went back. Right? So in order for it, when it diffracted, it maintained have a high velocity. It goes like this, and it goes like that, and it goes like this. But when it's reflected, this means that it had to stop. And when it had to stop, this means it's very, mathematically, it's very interesting. When it stops, it means that the velocity is equal to 0. Well, now, if I have the velocity at some given point equal to 0, and I have the velocity far from the target, this means I can calculate the change in the kinetic energy. Furthermore, if I add this to the change in the potential energy, which is equal to, when it's at infinity, it's equal to 0 potential energy. where it's at the distance d, that this potential energy is equal to Ke, Q1, Q2 divided by distance between them. So you see that the only unknown actually is this distance between the alpha particle and the atom. You understand? So I have the change in the kinetic energy, 1/2 mv squared minus 0, equal minus the change in the potential energy, which is equal to 0 minus Ke Q1 divided by d. I know Q1, I know Q2, I know Ke, I know the mass, I know the velocity. What is left is simply d. Okay? And now the trick is that when you calculate this d, and this is the huge surprise, when you calculate this d, you find that this d is very small, is much smaller than the atom. And that is a very important issue. So from this, we come up with a different way of viewing the atom. And that is, instead of having a sort of a jelly where the electrons are in the middle and the protons, because at the end, the atom is neutral. So I must have as many plus charges as negative charges. Okay? So instead of having these protons, which are distributed almost uniformly inside the sphere, now I am obliged to have these protons put in a very tiny space around the electrons, such that when it comes, it hits the nucleus of the gold foil. Okay, that this nucleus is really much smaller than the atom cloud around it. So now we have, okay, we're still on a spherical shape, but the electrons now are sitting in vacuum, there's nothing there, and all the plus signs are concentrated physically into a very tiny point in space. Okay, so now, of course, I would consider that the electrons are going around the protons. This was inspired by planetary models, but we'll see later on that actually they, I mean, at least from a Newtonian mechanics point of view, they have to go around the proton. Okay, so Newton, Thomson, Rutherford. Okay. Okay. Now we come to a different issue. So you can see that. I hope that you can see that you have an idea. You have an experiment. This experiment challenges this idea. You come up with something which is a bit more smarter and which explains this experiment. Then you have another experiment which challenges this new idea. And thus, you have to come up with a different concept that is enable you to explain this one, but also to explain this one, okay? And of course, to maintain this spherical shape of the atom. Okay. Now we come with what we're going to call the spectrum. And this is, of course, also a second surprise. So what scientists did is that, okay, we have this atom, and you have these small proton here, and the electrons are going around, like it's pretty much like in planetary models. Okay, great. Then how about we try to understand how they are formed? Okay, this is basically the goal of what we are doing. Okay, so what they do is that they have a small tube. They have a small tube. From this tube, they remove all the air, everything, all the air. So there's basically zero atom inside. And then they could put either hydrogen, for example, or mercury, or neon inside. So basically, I have a tube and a very tiny amount. Okay, and what they're gonna do is that they're gonna see how these atoms are going to radiate. Okay, and the surprise is that they see that they radiate not in a continuum. We come back to this idea of continuum and discrete, but rather in discrete spectra. Okay, and so we have a new challenge now, and that is basically the Rutherford model is unable to explain this idea. So basically, these electrons, which are around the protons, they are not around it in a more or less arbitrary fashion. There is some order, and this order is giving me these rays. Okay, it's giving me these rays, and of course, the fact that these rays are discrete and not continuous, it is an information in itself. So we have two information here. One is discrete, the discreteness of the spectrum. This is continuous. So it's not continuous, it's discrete. And the second information is, of course, these wavelengths that we see. This is, for example, ultraviolet, that's blue, that's green, and that is red. So for each one of these, I can determine the wavelength. Okay? So this is a challenge for Rutherford's theory. So Rutherford's electrons are undergoing a centripetal acceleration, and so should radiate electromagnetic waves of the same frequency. So basically, this means that we should a priori get something which is continuous, but we don't. We have something which is discrete. So if I have something which is discrete, the first thing that I'm going to do is see what are the wavelengths. So what did scientists do? What Mr. Balmer did is, okay, you know what? I'm gonna take these spectra here, you can see, okay, and I'm gonna see just the wavelength. So, for example, I'm gonna have 364.6 for 10.2, etc., etc. And now, what I'm going to do, I'm going to find a relationship between these wavelengths. There must be a relationship, okay? And I'm gonna see if I'm able to get a relationship only based on just simple observation, experimental observation, and a simple link between these wavelengths. And what Rydberg found, he found that I can predict, okay, the wavelength. If I have this n number, this integer number n, such that 1 over lambda is equal to some constant, I don't know what that is for the moment, it's called Rydberg constant, okay? 1 over 2 squared minus 1 over n squared, such that n is an integer and greater than 2. Strictly greater than 2, this means equal to 3, 4, 5, etc. Okay? So this is a formula which was obtained experimentally without any theoretical explanation. Okay? But we are still looking for another model. Okay? But in order to get another model, we need to get first the data well. Okay? And this is one of, you could take any atom that you have, any atom, this string between lambda and n still hold, okay? Considering that a different Rydberg's constant, okay? So for that, we have what we call also only via experiment, the Lehman series, where instead of 2, I have 1. So Lehman found I don't need 2, I can put 1. I have a different set of series. Balmer is for the first number here is equal to 2. Lehman is the first number is equal to 1. And then the Paschen is when this number is equal to 3. Okay. This is great. We have good experimental results, and we are able to at least to link these wavelengths. They are not arbitrarily distributed, but there is some order. And this order must reflect some physics. Okay, just a few words about the absorption spectra is that the same thing, if I detect what these atoms in my small tube are emitting, it's also the same as what they are observing. Yani, if I have white light and I put these tubes with, let's say, hydrogen, and I observe the spectrum of the white light on the back, what I notice is that the same rays as the one which are emitted are the one which are absorbed. So it seems that the atom, these electrons, they can absorb and they emit wavelength, okay, at exactly the same lambda, okay. So the lambda for absorption is exactly equal to the lambda for emission, okay. So what this means is that if I have to find an explanation, then this explanation must explain to me all these processes together. Okay. Just a few words about the usage of absorption spectra. It's usually done in astrophysics, and this is the sun. I'm going to skip that and go straight to our friend Mr. Bohr. Okay, so if you were in class, I would have asked you, why do you think I put Claude Bonnet water lilies in 1914, And Mr. Bohr, he obtained his Nobel Prize for the explanation of the atom in 1922. So clearly you can see this is the same era, right? The same era between the two. Okay. If anyone would like to answer, I would be happy to listen to. Why I have put Claude Monet and Niels Bohr? John Shaib. You have any idea? Are you guys listening to me or are you off? Okay, anyways. The reason why I put Claude Monet's lilies in this view, because it is a very important indication. Because you guys probably heard of the Impressionism. It's a art movement, okay, at the beginning of the 1900s, okay, which actually, like Claude Monet, you can see it clearly. He drew the lilas, this water flower, okay, but not exactly, okay. So it was like a step between the classic art and Picasso, which is basically the complete revolution, okay. And what Bohr did is he did something the same. That is, he has one foot into classical mechanics and another foot into quantum mechanics, okay? It's not the complete revolution of Heisenberg, but it's a good starting point, especially that with his theory of the atom, he was explaining all of what we discussed before, okay? So what is his model say? So what he said is that, okay, these electrons are not just sitting like this, but they are going around the proton. They are going around the proton. This should appear to you as a must. Why? Because if they are not going around the proton, then the only force which is in between the proton and the electron is the electrostatic force. If the electrostatic force, then this means that the electron must go towards the proton because it must be attracted towards the proton. Consequently, I will not have electrons which are in the neighborhood of the proton. However, if I have a proton, if the electron is going around, then I'm going to have the centrifugal force. Centrifugal force will point the electron away from the proton and could equilibrate the electrostatic force which is towards the proton. For an equilibrium, then this electron will go around the proton, will be able to go around the proton. So only certain stable orbits are stable. Why? Because if the electron is too far from the proton, then going at this velocity, then the electrostatic force is very weak, and this electron will go away from the proton. If it is too close, then the electrostatic force is stronger than the centrifugal force, and the electron will go towards the proton. Okay? Consequently, there are only special orbits for which these forces are equal and opposites. Okay? And so let's see, and then how do you explain radiation? Now it becomes relatively simple. The radiation, the absorption or the emission can now be explained in the simple transition of the electrons between these stable orbits. Okay? So radiation is emitted by the atom when the electron go from its absorption from 2 to 3, and then radiation that goes from 3 to 2. And since I have discrete orbits, then this explains the discreteness of the wavelengths. So one of the major accomplishments of Mr. Bohr is simply this relationship here, which is the E initial, the energy initially, minus the energy final equal to HF. So, and this is a link between the electron energy and the photon, which was actually seen, we have seen it with our friend Mr. Einstein, okay? So Einstein, he really said that the photon has an energy E is equal to HF, and now what Bohr did, he did the electron, he linked the electron change in energy to the photon which is emitted by this electron. Okay, so the light frequency emitted in the jump is related to the change in the atom's energy. So, but mathematically, his major assumption, okay, and so now if we have the electron which is going around the proton, we have electrostatic force, centrifugal force, they are equal. Right? This is all classical mechanics, but using classical mechanics, we cannot go far. We have to bring in quantum mechanics. Quantum mechanics is about quanta, is about quantization, is about integer numbers, okay? And what Boris said is that we have stable electron orbits are those for which the orbital momentum, which is mvr, that's the orbital momentum, is an integer multiple of h bar, where h bar is equal to h divided by 2 pi. We have seen h is the Planck's constant, okay? So what he did is he related MEVR, that's classical mechanics, the mass, the velocity, and the position, and the radius, okay? Equal to quantum mechanics, which is equal to NH bar. And N is called the principal quantum number, okay? So this is his major assumption. And from this major assumption, one can show, I'm not gonna go into the calculation, it's not required from you to know the calculation, but for people who would love to see that, then he would, then it's very easy actually to demonstrate that these radii, Rn, are linked to a constant n square multiplied by h bar square divided by the mass of the electron, Ke, which is the Coulomb's constant, and the charge of the electron. And now n is equal to 1, 2, 3, 4, etc. Okay? So for n equal to 1, we have Rn equal to A0, which is called the Bohr's radius, which is basically the radius of the atom. Okay? And A0, and one can show that equal to 0.0529 nanometer. Okay? Okay, if we take this radius and then we hook it to the energy to understand the energy, now we have a formula for the energy. Okay, where En is equal to minus the mass of the electron, Ke square, e to the power 4 divided by 2h bar square, 1 over n square, and now you can see 1 over n square, you have this 1 over n square here in the denominator. If I put now, put these numbers together, then I'm going to have that my energy En equal minus 13.6 divided by h. Okay? Now, and at the same time, so these are the two formulas that you must remember. The radius of the atom, of the electrons, of the stable electron orbits, goes n squared to the power A0. They multiply by A0. So for n equal to 1, Rn equal to A0. For n equal to 2, Rn is equal to 4 times A0. And for n equal to 3, Rn equal to 9 times A0. Okay? Now, in terms of energies, my energy is now equal to minus 13.6 eV divided by S. Okay? Now you're gonna probably, I don't know, probably you would have the question is that minus energy is minus. What does that mean? Where does this minus come from actually? Okay? Okay, the En is the total energy. Okay? What is in the total energy? There is kinetic energy and there is potential energy. This session will end, and I would like to continue for about 15 minutes afterwards. Okay? So I'm gonna stop now.